Have you ever noticed how a pencil dipped in a glass of water looks strangely bent at the surface? Or how your legs look shorter when you stand in a swimming pool? This isn't magic, it's physics in action. When a straight stick or pencil is placed obliquely in water, the part inside the water appears shorter and raised, as if it has bent at the surface. The reason for this illusion lies in the bending of light rays, a process we call refraction. Remember, the law of refraction tells us that when light travels from a denser medium like water to a rarer medium like air, it bends away from the normal. So, the point we actually see is not the true tip of the stick but a virtual image formed due to refraction. And that's why the stick looks bent. Let's take a closer look with the help of a ray diagram. Imagine a stick marked as XOP, with the portion OP dipped in water. Light rays from the tip P travel upward, moving from water to air. At the water surface, these rays bend away from the normal due to refraction. When these refracted rays enter our eyes, our brain extends them backward in a straight line. The rays appear to come from a point P', which lies above the real point P. So instead of seeing OP, we see OP', the submerged part appears raised. This makes the whole stick XOP appear bent at the surface. As you can see in the diagram, the straight stick now looks as if it's broken at the waterline. Now let's explore the physics behind this apparent shift. What our eyes see is not the real position of the object, but its virtual image. The apparent depth is always less than the real depth. This relationship is given by the formula apparent depth equals real depth divided by refractive index. For example, the refractive index of water is 4/3. So, if an object is placed at a real depth of 12 centimeters, it will appear at only 9 centimeters depth to an observer in air. This is exactly why the floor of a swimming pool looks much shallower than it actually is. From this, we can state a general rule. Whenever an object lies in a denser medium like water and is viewed from a rarer medium like air, it always appears closer to the surface than its actual position. For instance, a coin placed at the bottom of a glass of water looks raised. That's because the light rays bend away from the normal as they emerge into the air. This rule is beautifully summarized by the relation refractive index mu equals real depth divided by apparent depth. So next time you're at a swimming pool, remember, the water hasn't magically vanished. It's simply the physics of refraction playing a trick on your eyes. But what happens in the opposite case? Suppose you are underwater, looking at an object in air. In this situation, light rays travel from the rarer medium, air, into the denser medium, water. This time, the rays bend towards the normal. As a result, the object in air appears higher than its real position. For example, a lamp post viewed by a diver underwater will seem lifted upwards in the sky. So the apparent shift depends on which direction you are observing. From air to water, objects appear raised. From water to air, objects appear higher than their actual position. Let's solve an example. A coin is placed at the bottom of a tank filled with water of refractive index 4/3. If the real depth is 1.2 meters, we are asked to find the apparent depth and the shift. We use the formula apparent depth equals real depth divided by nu. Substituting the values, apparent depth equals 1.2 divided by open bracket 4/3 close bracket. That works out to 0.9 meters. Now, the shift is simply the difference between real depth and apparent depth. So, shift equals 1.2 minus 0.9, which gives 0.3 meters. This means the coin appears raised by about 30 centimeters. The diagram shows both the actual and the apparent positions. Let's quickly recap what we've learned. We discovered that the bending of a stick in water is due to the refraction of light. The submerged portion always appears raised because the apparent depth is less than the real depth. We connected this with the formula refractive index mu equals real depth divided by apparent depth. This concept explains everyday experiences, from coins at the bottom of a glass to fish appearing closer to the surface to the shallow look of swimming pools. Even in spearfishing, hunters must aim slightly below the apparent position of the fish to hit it correctly. So, refraction doesn't just bend pencils in water, it shapes our entire visual experience of the underwater world. I hope you now clearly understand why objects appear bent or raised underwater. See you in the next session, where we'll explore yet another fascinating property of light.